I'm going to be explaining for you the minimum path sum problem, medium problem from LeetCode. Given the n by n grid filled with non-negative numbers, find a path from top left to bottom right which minimizes the sum of all the numbers along its path. You can only move either down or right at any point in time. And so for in this example, you could either go right, or you could go right and down, or you can go right, down, or you can go down, right, or go down, right, down, or whatever, as long as you're going either right or down. But the minimum path is going to be this one here, because the sum across all of the nodes is going to be the smallest amount out of all these paths. And so when you see some sort of optimization problem that asks for minimizing something like this, then you're sort of thinking about dynamic programming. But one other hint that you could get is the fact that there are some overlapping subproblems. For instance, to get to each node, we're gonna have to find the path this way, and this path will have to involve finding the path this way and this way, which would have already been found by doing this path, which is going that way as well. And you're sort of getting into the point where you're sort of recalculating things, and you don't want that. So you can sort of make a recursive relationship where you can record the recursion and how it works, and then sort of save the values into the smaller problems and memorize them so that you can build up a larger solution. So for instance, we can have a function called path ij, which finds the minimum sum to a given point ij. So in this case, if we want to get to 0.11, it's going to be the minimum of if we had done right and down or down and right. We want to find the smallest of that. So it's going to be that plus the paths from how we started. So it's going to be we know that for a fact that if we're at a point here, then we had to either come from above us or from the left of us, because we can only go down or right. So it's going to be equal to grid ij plus the minimum of the path from the left of us, which would be I and j minus 1, versus the path that came to our right. So that would be above us. So that would be path of I minus 1 j. So, and we're going to, obviously, we need to add the value that we're currently at to that. But that's generally all that we have to do to find our recursion. And we can do this top down by working from the very first value, or we can do it bottom up by doing it from the starting point, the end point that we're reaching, and then working our way back to the beginning of the array. It really works either way because we're going to be doing it iteratively anyway. But let us begin. So let's have a int structure. We're going to have two-dimensional because of the way the problem is set up. We're going to call it dp, and we're going to set it equal to grid.length and grid0.length, and that's going to instantiate our dp array matrix, which will be set to the dimensions of the matrix. Okay, so let's now say we want to return. Our return type is going to be return dp, and the answer is going to be stored here because we're going to calculate this. So it's going to be grid.length minus 1 grid0.length minus 1. That's going to be where our answer will be stored, because we're going to be finding out how we got to this point from the beginning. And now we're going to be, and if you were going to be doing it from bottom up by starting from here and working your way up, it would have been exactly the same logic. You just had to reverse it, and you would be looking for the dp at 0, 0. So either way works. So let's do a for loop iterating through the rows and the columns. So let's start with the rows. So for int I is equal to 0, I being less than grid.length, I plus plus, and then we're going to have an embedded for loop to do the columns. So j being less than grid0.length, j plus plus. Okay, great. Now we're at this point here, and we want to say, okay, so if I is greater than 0, and j is also greater than 0. In fact, before we do that, we want to declare dpij to just simply be the path that we stepped onto, whatever we stepped onto at that point, because we're going to have to add that to the final result. So if I and j are greater than 0, then we're somewhere in the middle of the table, somewhere like within the table. So then that's going to be, so dpij we'll just add onto that the minimum. That's going to be this part because we've already written this part here. That's just going to be the minimum of dp, so we could have either come from above or we could have come from the left because we can only go right or down. Okay, vice versa. So let's then say, okay, else if I is greater than 0. Okay, so in this else case, this is going to assume that we're in the very first column, but not necessarily in the very first row. We're going to be, if I is greater than 0, and we're in this sort of column here, then we had to only have come from downwards. So dp ij will add onto that dp of I minus 1 j, because we could have only come from downwards if we're in the first column. Okay, else if j is greater than 0, which would mean that if we manage to pass through this, then we know that one of the two variables is equal to 0. In this case, I would be 0, so we're in the very first column now. First row, sorry, meaning that we could have only come from the left-hand side. So dpij will just add onto that the value from the left-hand side, because that would be the equivalent of going right. And then that's really all we have to do, because then all we're going to do is return our end value. Yeah,